projects. In this video, we are going to explain about the project that is interpretable prediction of a decentralized smart grid based on machine learning and explainable artificial intelligence. So before getting into the execution, first let us understand what is the project about. So what is smart grid? That is the decentralized smart grid. It is basically a modern way of managing the electricity where power isn't just generated in big central stations, but also it comes from smaller sources like solar panel, wind turbines, and even individual households that can produce and share energy. So this makes the system more reliable and also flexible because energy is generated and consumed closer to where it is needed. But here the challenge is renewable energy, like solar and wind, doesn't always produce power constantly. Sunlight and wind can change throughout the day. The variability makes it harder to keep the grid stable. Since supply and demand have to be balanced in real time, that's why new methods and smarter systems are needed to ensure electricity stays stable and also available whenever people need. And we do have some traditional methods. So, traditional methods they struggle to deal with the huge and constantly changing data produced by smart grids. That's where machine learning comes in. It can find hidden patterns in the data and make accurate predictions about whether the grid will remain stable or not. Here, the problem, however, it is that many machine learning models work like a black box. They can give answers, but they don't clearly explain why or how they reach those answers. In energy systems, this is a big issue because engineers and operators need to trust the system and also understand the reasons behind its predictions. Without the clarity, it is difficult to rely fully on machine learning for critical decisions in managing the grid. So, to deal with these challenges, we need prediction models that don't just give us accurate results but also explain how they work. This way, people who manage the grid can see which factors matter the most, like how quickly the system reacts, how much power is being used, or how sensitive prices are to changes. Understanding these details helps in making predictions and making better decisions and keeping centralized smart grid stable. So here, to overcome with all these issues, the system we are building is designed to predict whether a decentralized smart grid will stay stable or not. So it is to predict whether the decentralized grid system will stay stable or not. To do this, we use dataset that was created through simulations of four-node star network and made publicly available in the UCI machinery repository. So the dataset which is produced through this four-node star network that is simulated and that dataset is published in the UCI and we have used that dataset. So the dataset gives us the foundation to train and test the different machine learning models to make predictions. And here, to make predictions, we have applied 10 well-known machine learning techniques that is adaptive boosting, AdaBoost, artificial neural network that is ANN, gradient boosting that is GBoost, KNN that is K nearest neighbor, logistic regression that is LR, naive Bayes, random forest, stochastic gradient descent, support vector machine, and extreme gradient boosting. And here we then compare their performance using evaluation measures that are accuracy, precision, recall, FN score, and cumulative accuracy. So by doing this, the system not only aims to make accurate predictions but also ensures that the results are transparent and useful for making reliable decisions in smart grid management. So this is not the complete solution for the project, that is predicting stable or unstable of the grid control system. Because machine learnings, that is machine learning models, they often work like black box. That is, we get result, but we don't know why the system made that decision. So to solve this, this project uses special tools that are explainable artificial intelligence techniques that are SHAP and LINE. These tools act like translators. They break down the model predictions and show which factors had the biggest impact on the outcome. For example, they can show whether the grid's reaction time, the amount of power being used, or how sensitive prices are to the changes played a major role in deciding if grid would stay stable or not. So this way, the system doesn't just give a prediction, it also explains the reason behind it, which makes the results more trustworthy and useful for decision makers. And to make the system even stronger, here we have incorporated stacking classifier. So here we have used hybrid stacking classifier that combines strengths of different machine learning models instead of relying on just one. Think of it like forming a team where each member has unique skills. Here we have incorporated bagging with random forest, ADA boost, and bagging with k nearest neighbor along with the light GVM. Were all brought together. So by stacking them, the system can make more reliable predictions because it learns from multiple perspectives. Here we have also included a user-friendly web interface. So here we have developed a web interface using Flask framework so that anyone can interact with the system easily. Instead of working with raw code or dataset, users just enter the required value into the interface and the system instantly uses the trained models to predict whether the smart grid will stay stable or not. This makes the project not only more powerful in terms of performance but also much more practical and user friendly. And moving on to the implementation. To implement, we have followed the steps which are mentioned in the flow of work. So first, we have imported all the necessary Python packages needed. That is for data handling, machine learning, XAI, persistence, and web framework. Then comes loading the dataset. So here, we read the publicly available DSGC simulation file into a data frame so we can inspect and use the data. Then comes exploring the dataset. Here, we check the data size, types, missing values, and few sample rows to understand what we have. Then comes pre-processing. So here we clean and transform the data. That is, we fill or remove the missing values, scale or encode the features. So it is ready for the models. Then we split the data into train and test sets. Training set is used to train the model and testing set is used to evaluate the model. And here comes model training. Here we will be training all the models for predicting whether the grid system, that is the power, will stay stable or not. And then we evaluate all the models using accuracy, precision, recall, and FN score. And those those performance scores will be visually represented through graphs. After that, we will be selecting the best performing model and saving it for the future use. And coming to this XAI part. So here we run explainability tools that are Sharp and Lime to show which input features most influence the predictions. And coming to the front end part, here we built a simple web UI with a user registration login backed by SQLite so users can access the predictor. And in the front end, users they can give the feature values. It will be pre-processed at the backend. It will be fed to the train model. Then train model will be giving us the prediction. So this is how we have implemented the project. Moving on to the algorithms used. So these are the algorithms used in the project. This is the extension model, and these are the 10 different models using which we have predicted the electricity that will be stable or not through the smart grids. To implement this project, we need two kinds of requirements, which are hardware and software. In hardware, we need operating system of Windows, processor of 5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Software are application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is the overview of the project. Now let's execute it. To execute, let's open the code folder of the project. So these are the source code files of the project. Here in this folder, we have the dataset that is used. So let's open it. So this is the dataset. So this is the dataset. Here are the variables. These are the attributes using which we will be predicting whether the network will be, that is the electricity will be stable or unstable. So these are the independent attributes which will be dependent on this one. Let's close this, get back. And in this folder, that is the model folder, we have the algorithm information stored that will be loaded into the project code during runtime of the application. This is the static folder in which we have files related to CSS, JavaScript, and Bootstrap files, which are important for the visual appeal. And here is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And this is app.py file. So this .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. This is the notebook file. It's a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, which makes it a popular choice for the data science. And this is the sample file in which we have test cases that we will be using in the front end for prediction. This is the signup.db file. This file is a database file which is used to store the user information. So this is all about the code folder. Now let's execute. Copy the path of the code folder. So copy it. Now open Anaconda prompt. It is open. Give the command cd, give the space, paste the copied path. Now click on enter. Here you can observe current directory is changed to the code folder's path. Now compile app.py file by giving the command python space app.py and click on enter. So this command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address. So this is the address where application has been hosted. So here, this is the local host and this is the port. So at this address, application has been hosted unless configured differently. So now we have to copy this local link provided by the Flask framework and paste it into any web browser. I have copied it. I prefer Google Chrome, so I will paste it in that. Paste the link here and now click on enter. So this is the web page of the project, which is displayed in the browser. And this is developed using Flask framework. So we need to get signed up first. Click on sign up and enter all the registration details to create the account. I have already registered, so I will directly sign in. Click on sign in. Give your username and the password. And now click on sign in. We have signed in successfully and redirected to prediction page of the project. So this is the prediction page. And now click on prediction. So here you can see values, right? So these are the parameters need to be given as input for predicting whether the electricity will be stable or not from the grids produced. So here we have multiple parameters. So the first one we have is TAU1, TAU2, TAU3, and TAU4. So these are the tau1 to tau4. So these represents the reaction times of the four nodes in the smart grid. They indicate how quickly each node responds to changes in the supply or demand. And then here we have P1, P2, P3, and P4. So these are the nominal power values of the four nodes showing standard or rated amount of the power each node can generate or consume. Then we have G1, G2, G3, and G4. So these represent the price elasticity or gain coefficients at each node, indicating how sensitive the system is to the changes in the electricity prices or the grid signals. So this is all about the parameters. Now let's enter them. For that, we are supposed to open the test cases. So let's open them. Open the sample file. So here are the test cases. So let's apply filter to the column that we will be predicting. Apply filter. So let's apply filter to stable class. Click on OK. And let's try with the first case. So the T1 value is 2.00 and then T2 is 2.311. T3 is 4.44, that is 4.10. T4 is 2.72. P1 is 4.39. P2 is minus 1.53. P3 minus 1.32. P4 minus 1.53. G1 is 0.05. G2 is 0.57. G3 is 0.61, 0.061 that is. And the next we have G4 0.77. Click on predict. So this given information, it will be pre-processed at the back end. It will be fed it to the train model, and then train model will be giving us a prediction. So here we got the prediction that it is stable. The system predicts the current configuration is stable. So you can proceed with the confidence as the parameters meet the required stability criteria. So here we got the prediction as stable. Let's try with some more. Click on back. Now let's check with this case where T1 is 6.62, T2 is 6.84, T3 is 4.21, T4 is 1.81, and P1 is 4.58, and P2 is minus 1.81, P3 is minus 1.38, P4 is minus 1.3805, G1 is minus, that is 0.37, G2 is 0.127, G3 is 0.83, G4 is 0.39. Now click on predict. And here we got the prediction that it is stable. Here we got the electric grid, I mean electricity produced from grid is stable electricity. Now let's try with the other case. So apply filter to unstable. Click on OK. Click on back. So let's check with this case where T1 is 1.9531, T2 is 9.69, T3 is 6.57, T4 is 7.73, P1 is 5.12, P2 is minus 1.86, P3 is minus 1.38, P4 is minus 1.888, G1 is 0.48, G2 is 0.93, and then G3 is 0.43, G4 is 0.32. Now click on predict. Here we got the result that is unstable. So here unstable electricity has been predicted. The system predicts the current configuration is unstable. So please review your input values and consider adjustments to achieve stability. That means these parameters need to be adjusted to get the stable connection. Let's check with the another case. Click on back. So here T1 is 3.38, T2 6.73, T3 is 3.11, T4 is 3.777, P1 is 2.66, P2 is minus 0.92, P3 is minus 0.61, P4 is minus 1.12, G1 is 0.28, G2 is 0.38, and G3 is 0.65. Last G4 is 0.91. Now click on predict. So here we got the prediction that it is unstable. So this we got the prediction as unstable. So this is how you need to do the prediction. Now let's check with the graphs. Click on about. And here the first graph we have is the sample outcome graph. This is the sample outcome graph, which shows the distribution of the predictions that we are doing. That is the classes we have. So this is the ROC curve and this is the sample. So let's click on view image. Click on view image. So here blue represents unstable and orange represents stable. Here if you see there is class imbalance because 63% is unstable and 36% is stable. So let's close this. And here we have correlation matrix. So click on view image. So this shows the correlation between individual variables. Close it. And here we have ROC curve graph. So this is the ROC curve graph. So we are done with the visualizations. Now let's see with the sharp plots. Click on sharp plots. So here we have sharp value for class 0, that is stable connections. And here we have for class 1, click on view image. Click on view image. So this is sharp value for class 1. Close this. Now let's see the metrics. So here we have AUC score, accuracy score, precision score. Let's click on view image. Here on x-axis, we have all the models that we have trained, and on y-axis, we have accuracy score. So this is the cumulative accuracy score. Let's close this. Similarly, we have recall score, F1 score, AUC score, and precision score. Now click on sign out, that is log out. So by combining machine learning with the explainable AI models, the system not only predicts the stability of a decentralized smart grid, but also shows which factors are driving those predictions. With a user-friendly interface, anyone can provide input and get the insights into the grid's behavior. This makes managing smart grids and more reliable, transparent, and practical, helping us to move towards a more stable and sustainable energy future. So this is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.